Alan Alda, and in that show, a recurring theme shows Hawkeye and BJ drinking from their still. But they are distilling alcohol, in particular they're distilling gin, and then they're drinking it to make themselves happy. They sometimes joked about putting lemon drops into their gin and stuff like that. Well, gin is a tea made from ethanol and water, in which certain fruits and vegetables are allowed to infuse into the alcohol. Things like juniper berries and lemon peels and cinnamon stick and cardamom and those sorts of things. Anyway, what I'm going to show you today is not how to make gin, because that actually happens to be a federal offense, but how we distill ethanol from some solids. In other words, how do we separate a mixture that's a solid and a liquid, where what we're interested in is the liquid. So what I have here is a round bottom flask. It's a 100 milliliter round bottom flask, and I've put some magnesium shavings down on the bottom. Magnesium is good because it reacts with water and it will dry the ethanol. We're going to do everything really fast, but imagine this is a cooking show, and so if we waited longer, we could affect that transformation that we're interested in. So I have some ethanol here, and I'm going to pour it into the round bottom flask. And again, the round bottom flask already contains some magnesium shavings, and being a round bottom flask that's 100 milliliters, you can put 50 milliliters or so in. You never want to fill the flask more than half filled, and the reason is, as it becomes more than half filled, the surface area that's exposed to the air, or exposed to the air, gets smaller and smaller, and you have a greater probability of bumping it, which means to superheat it, and when it superheats, it goes all over the place. It just literally bumps. So that's so it's a good idea not to go more than half filled. If you have much more than 50 milliliters to distill, either get a larger round bottom flask or distill it in more than one part. In other words, pour in half of it and then come back and after you've distilled some off, pour in some more. Okay, so we have an adapter, and we have the thermometer adapter. And this is a thermometer. You have to make sure that the thermometer goes up to at least as high as your liquid boils. If you don't go high enough, so in other words, this is 110, it goes up to 110. Ethanol boils at 78, so that's going to be fine. But if we were distilling something that boiled above 110, you'd have to get a thermometer that's above 110. Otherwise, you run the risk of breaking the thermometer, and breaking a mercury thermometer that way is a bad idea. Okay, so you put this all together and you adjust the thermometer so that the bulb is even with this side arm here, so that the mercury bulb is even with the side arm. That looks a little low. It's not absolutely crucial that it be exactly at a certain point, but you want it so that the bulb is going to be bathed in the vapor, and I'll show you that when we start to heat it up. Okay, so this is a condenser, and I've connected some Tygon tubing to it. One end goes to a water source. Cold water is important to use here. If you use hot water, you're not going to get the effect you want. And then the other end just goes to the sink to dump out. So water comes in through the bottom and goes out through the top. And that's always the case. Whenever you have a condenser, you always run the water in through the bottom and out through the top. And what a condenser consists of is it's a tube. You might be able to see down this tube. Okay? And then jacketed about this tube is more glass, and the water runs in the jacket. So the vapor, what we're trying to distill, is going to go down the middle, and then cooling water is going around the outside in what we call the cooling jacket. So we'll assemble that part. And then another adapter, and down to our receiving flask. And sometimes it takes a little bit of adjustment to get everything working right. Now, if you have clamps available, and they make these plastic clamps that clamp these joints together, that's a good idea. And you can also grease the joints if the grease is not going to contaminate your material. So if the grease is not soluble in your material, you can go ahead and grease the joints. But that's not really crucial. I think if you have everything put together fairly tightly, everything's going to be fine. So I'm going to connect the bottom end of the condenser to the cold water source with through a piece of plastic tubing, and now I can start to apply the heat. Now, when you do distillations in the laboratory, in fact, when you heat almost anything in the laboratory, it's a good idea not to use a Bunsen burner. Bunsen burners are fine for doing things like flame tests, but in general, an open flame is dangerous because you can ignite the vapor. So what we're going to use is something called a heating mantle, and this is a heating mantle. Basically, it's a resistively heated coil, and it's a much safer way to heat our still pot here. And it's connected to a controller, so it's a good idea not to plug these directly into the wall, because if you plug this directly into the wall, you're running 115 volts through it, and it's going to get really hot really fast. So what this does is it sort of turns on, turns off, turns on, turns off, and that's how you can control the temperature. You can also use something called a variac, which just decreases the amount of voltage excuse me, that you run through this thing. So, and those are big blue, almost like electric train controllers. Okay, so we're going to raise the heating mantle up into place so that it's nice and snug against the bottom of the round bottom. If you're heating something that's relatively difficult to boil, you might want to add some fiberglass, we call this glass wool, around the top to help insulate it, keep the heat in a little bit better. We can put aluminum foil on top of this if we want to insulate it even more. And then let's just turn this on. So we're going to turn the knob, and we'll just set it to something modest. And we'll have to adjust that as we heat it up to make sure that we get the heating rate that we want, so we get the distillation rate that we want. Okay, now, so we're starting to heat. Let me make one last point before I sort of break from the camera and let this get up to temperature, and that is, it may look like we're heating a closed system here, and obviously heating a closed system is a bad idea. Charles's law says that if you heat something in a closed, constant pressure, the volume is going to go up, and obviously if the volume of the system wants to go up, it's just going to blow itself apart. You never heat a closed system. But this adapter over here, attached to the receiving flask, has a little side arm, and this side arm is open to the air. If you're worried about exposing your liquid to the air, you can connect this to a nitrogen line that has a bubbler on it, and that would allow you to heat it in the absence of air, but still not have it be a closed system. A bubbler is a device that allows it to regulate the pressure so that the pressure never gets much above 1 atmosphere. And again, obviously you don't want everything to get above 1 atmosphere, because then you run the risk of having it blow itself apart and breaking the glass and causing a general disaster. Okay, so what we're doing now is we're going to wait for this to come up to temperature, and we're going to break for a bit. Oh, I forgot to turn on the water. Okay, it's a good idea to turn on the water. What does the water do? Well, the water is going to cool the vapor. Once we get it going, that'll be obvious. You don't need the water on very high, so you can see that it isn't on very high. Having the water on very high just invites disaster as well, because the water pressure could cause some of these hoses to come off. If you're concerned about it, you can always use copper wire to wire these on, making a mess. Make sure that's in the sink. Okay, so now we'll let this come up to temperature, and then once it's actually distilling, I'll come back and tell you some more. Okay, so we've got a gentle reflux going now inside this round bottom flask, and reflux, again, is just sort of a gentle boil, and the vapor rises up into this section here. It equilibrates with the thermometer, so the thermometer should read the boiling temperature of ethanol. Today it's reading 77.5, and the literature says that ethanol boils at 78, so that's pretty close. Could be that the thermometer is not calibrated correctly, could be that the atmospheric pressure is a little bit low today. So the vapor now travels up here, equilibrates with the thermometer, and then it makes its way through this side arm, and then it hits the cold region of the condenser. And when it hits the cold region of the condenser, it starts to condense, and as the vapor makes its way through here, it gets colder and colder, so it condenses more and more, hence the name, and eventually it comes out the end here, goes through this adapter, and it drips into our receiving flask. What are we doing? Again, we're affecting a separation. We have solid and liquid on this side, magnesium and ethanol, and on this side here we have just the pure ethanol. If we were trying to separate two liquids, we could do the same thing, provided their boiling temperatures are not too close together. You can heat them up, and then according to the equations, we have that the lower boiling fraction should come off first. We may have to add another straight segment between here and here, so between this section and the round bottom flask, to give us more what we call theoretical plates. We just get better separation when you're trying to separate two liquids that way. And finally, if you did try to separate two liquids, it might be a good idea to either stir the solution with a magnetic stirrer, or add something like a boiling stone or a bumping chip to keep it from superheating. The magnesium is basically serving that role in the present separation. Now, what we're shooting for is something on the order of about a drop a second. Maybe you can go a little bit faster than that, but you don't want to go a lot faster than that. And so this is doing at a very nice rate. Again, what do? We can affect a separation between a solid and a liquid, where we're interested in the liquid phase by something called a distillation, or we can separate two liquids by a distillation, and this is a very common technique. It is exactly the way that you would make gin, except instead of magnesium shavings, you'd use juniper berries and lemon peels and other nice spices. And again, don't do this because don't make your own gin because it's against